Okay, so good morning or afternoon or evening, depending where you are. I'll talk today about transition metal KH spectral shapes. So I'll try to do give a short overview of the analysis of the KHs of transition metals, and then I focus specifically on the screening of the core hole. So I have 3 topics. And then I'll put breaks in between the 3 topics. First, I'll discuss pre-edges, then the edge spectral shapes, and then non-local screening peaks and pre-edges. But first, maybe to give you some idea where I am. I'm at home in Nijmegen in the Netherlands, so that's in the east of the country. People who are not familiar with the Netherlands landscape. So I work in Utrecht, which is in the middle, close to Holland. But I live in Nijmegen. I've shown 2 pictures of Nijmegen. On the top is the old Novium Magum, so the Roman city 2000 years ago. And the red arrow indicates where I'm actually sitting. So I'm sitting in the old fortress of Emperor Augustus in Nijmegen. Then the picture at the bottom is a picture of the oldest building of the Netherlands. It's more than 1000 years old. And that was built in memory of Emperor Theophano, who died in Nijmegen in the year 991. So she was the empress of Europe at that time. So now, 1000 years later, I'm living in Nijmegen. So back to science. Metal KHs. So the interpretation of metal KHs is initially quite straightforward. You have excitons, which you can reach by quadrupole transitions, and you have the edge jump, which you can reach by dipole transitions. So that's qualitatively the interpretation actually of every X-ray absorption spectrum, but not always you see the excitons and not always you see the edge jump. But this in metal KHs you see both, so both are quite clear in the experimental spectra. So these are some experimental spectra we published 15 years ago. These are iron oxide reference spectra. So you see very clearly the pre-edge at around between 71110 and 71115. So the one has 3D transitions. And then at higher energy you see edge jump. So in the edge jump you see the nice qualitative difference between iron 2 at shifted by 4 electron volts with respect to iron 3. And in the pre-edge region, you also see this shift. So you see a 1.5 electron volt shift between iron 2 and iron 3. And you see a big intensity difference between the octahedral blue line and the tetrahedral green line. So qualitatively, you can analyze these spectra already quite. You can get a lot of interesting information just from qualitative analysis. If you think these spectra are rather sharp, that's because they are K-beta detected HERFD spectra at the ID 26 at the of the Israel. I will not mention this. I assume Peter Glatzel will talk about this in much more detail. So the normal XANEs, you see the pre-edge weakly and K-beta detected XANEs, you see much more intensity and a much sharper version of the almost same spectrum. For the moment, I assume it's the same spectrum, K-beta detected XANEs. So qualitative analysis you can do very nicely also in the lab. On this graph, I put on the horizontal axis the centroid position. So of the pre-edge, so at 7112 EV, you see iron 2 plus, and 7113.5 iron 3. And on the vertical axis, I put the integrated pre-edge intensity. So that is a bit more tricky because you have to subtract the background of the edge and then integrate the pre-edge. And then at the bottom, you see the octahedral sites, and at the top, the tetrahedral sites. So the tetrahedral sites break inversion symmetry and have much more intensity. So by these 4 references, you can then do analysis. So we looked at the catalyst, iron complex in a zeolite. And then the blue points are different catalysts. And for the conditions we use, I'm not going into the specific conditions. All the iron remain 3+, as you can see from the position of the pre-etch, but the coordination changed almost from octahedral to almost tetrahedral, depending on the condition. So all these measurements were done operando at working conditions of the catalyst, long time ago, published 16 years ago. So this is just a qualitative analysis of the pre-etch. Before switching to theory, so the pre-etch, the position gives you the valency and the intensity gives you the symmetry. Now, how do you interpret the pre-etch? So you start from a ground state, which is approximated transition metal ionically, so it's a certain number of 3d electrons, 3dn. I assume the 4p is empty, and then you can make a pre-etch excitation, quadrupole excitation to 1s1 3dn plus 1, so you directly excite the 1s electron to the 3d band. That I call pre-etch, and then the etch is a 1s dipole transition to a 4p state. So that gives you the nice difference between the exciton pre-etches and the etch excitations. If you look at a certain number of pre-etches, these are all oxides, and then 3d, 4, 5, 6, and 7. It's manganese 3 oxide, manganese 2 oxide, iron 2 oxide, and cobalt 2 oxide. That's not so important. It's more important that you see the agreement between the experiments and the calculations. And these calculations are multiplet calculations. So you just assume that the ground state is 3dn and the final state is 1s 3dn plus 1, and you calculate the transition and you get these features. If you do not believe these multiplet calculations, I'll show that later. So maybe a short intermezzo with soft X-rays, that also will come back later when I switch to the etch. If you look at 2p X-ray absorption and 2p photon emission, you describe a transition metal oxide or compound in the ground state in the middle. So you have a 3d5 ground state for iron 3+, for example. And then you make an excitation to 3d6 ligand hole with charge transfer excitation. So you move an electron from the oxygen to the metal, and the energy difference is called delta, the charge transfer energy. If you're then going to do 2p X-ray absorption, which I will not discuss today, but just the energy effects, then the ground state 3d5 goes to 2p5 3d6, and the 3d6 ligand hole charge transfer state goes to 2p5 3d7 ligand hole. So you move a 2p electron to a 3d state. X-ray absorption is a self-screened experiment, so the energy difference in the final state, delta in the final state, is the same as delta in the initial state. This is completely different from photon emission, 2p XPS. Then you excite an electron, a core electron, out of the system. So your d5 ground state goes to 2p5 3d5, and your 3d6 ligand hole goes to 2p5 3d6 ligand hole, and the electron is somewhere in the continuum. Now this has enormous effects on the energy states. So the d6 ligand hole state is cooled down by the core hole potential Q, which is very large, something like 6-7 electron volts, and that means that the energy ordering of the states inverts. So this was a soft X-ray intermezzo, but now I switch back to K-etches, because this is exactly the difference between the pre-etch and the etch. The pre-etch is a self-screened quadrupole excitation, so it's a 1s 3D excitation. And you can use multiplet theory again because it's self-screened, so in first approximation you can forget about all screening. The etch is completely different. So now you excite the 1s electron to epsilon p, which is a free electron at p character, which can be anywhere in the empty state. So this is the etch excitation. So you can see from this graph that pre-etch and etch analysis will be theoretically completely different. Before switching to the etch, I'll just finish the pre-etch. So we saw before the pre-etches analyzed with multiplets, and you can very nicely make this visible if you do a Riggs experiment, which is given in blue. The experiment is given on the left, so that's a 1s2p Riggs experiment on cobalt oxide with a resolution of 200 milli-electron volt. This was done by Georgi Vanko 15 years ago, never published because the paper was never accepted, but he published it a few years later in another paper. And then you can nicely see that the multiple calculations of the 1s excitation and the 1s2p X-ray emission are reproduced by the calculations in the middle blue screen, confirming the fact that you can analyze the pre-etches with multiplets. So my conclusions of the first part of the pre-etches is that so qualitatively you can analyze the pre-etch. Position gives valency and intensity gives symmetry. If you do a theoretical analysis, you can say that you can calculate the 3D states with time-dependent DFT. But if you do HERFD, then the DD interactions are revealed and you see effects which you cannot calculate from time-dependent DFT. So at the bottom I put a warning for theoreticians. Time-dependent DFT and beta-salpeter are one hole, one electron calculations, which contain probably 90% of the pre-etches, but they miss part of the DD interaction. So some the details are not exactly reproduced. Okay, so this maybe is a good point to have a first break for questions.
All right, I'll remind everyone to type their questions into the chat. We've got one question. How do you properly define a background function to subtract from the K-edge so that you can isolate the pre-edge peaks?
Yeah, that's a that's a good question. Maybe some other people in the audience are more expert on that than me, but
I know that often there's the traditional arctan subtraction. Here we go. So they usually use an arctan.
Yeah, I would say if you do the same subtraction in every spectrum, then you make the same approximation, so that then at least consistent, you have a consistent result. I don't know if there's a depends also a little bit on the systems, if you have molecular systems or solid sampling.
I see. Okay. All right. Very good. Thank you, Frank. You should continue.
Okay. If there are no questions, I'll continue with the edge. So edge interpretation is quite different. So now you say I make a excitation from the 1s core level to an empty state. These are some calculations we did 10 years ago. Amelie Juhain did experiments on lithium cobalt oxide and calculation. So on the left is a experiment. The cobalt K-edge of lithium cobalt oxide, so it's 7710 is the pre-edge, very small here. Then at 7715 the edge starts. Again, both the total fluorescence field and the HERFD spectrum are shown, so you can see the nice improvement in resolution of the HERFD. And on the right is a calculation. This is LDA plus U plus the core hole potential. It's not perfect, but it gives a reasonably good description of the experiment. So peak A you can see in both, and then B and C are the two small peaks in the HERFD, and peak D is the first peak in the some of the white line of the fluorescence. So this is an example, and I think almost everybody, or maybe everybody, is using this approach, that you can assume that the K main edge can be calculated from the empty states, and then the only goal is to calculate the empty states, and then there are many different programs available. I think almost everybody initially starts, or at least calculates, with density functional theory, and then you have three choices. for the method. So multiple scattering, FEFF, FDM, and S are probably the most used. Band structure codes like Wien2K and quantum espresso, and real space density functional, especially if you work on molecules, Amsterdam density functional or Orca. But they all give in principle the correct result if you do the correct calculation. At least that's the assumption. But there is a problem, and that's this. If you do 1s XPS, you excite 1s electron, so it's the same 1s electron, out of the system. And this is the theoretical analysis I'll do first, and then I'll switch on the effects of this on X-ray absorption. So in the middle is a cluster calculation. That's a normal charge transfer multiplet calculation, where you take into account multiplets. But the multiplet effects are very small in XPS, so they're the green arrow, so they're actually not visible, they just broaden the lines. And the individual lines are different screening states. So the peak at the lowest energy is the D10 state. This is nickel oxide as an example. And then the peak at 8318 is the D9, and then the highest peak is the D8. So you have the three final states of nickel oxide, split by different screening. So the purple arrows indicate ligand metal charge transfer, and then you have your three states. But XPS has very strong screening, much stronger than X-ray absorption. And that you can see in the theoretical graph at the top. So then, in addition to the impurity model, you do dynamical mean field theory on the after the density of states, and then you project the results onto your cluster. And effectively, this is not theoretically not exactly correct, but I think for me it's the easiest way to see it is you get a new peak due to metal-metal charge transfer. So charge in the screening process is transferred from one nickel to another nickel, and that gives you an additional peak, actually at lower energy than the original peak. This screening channel is not present in X-ray absorption. It's normally weak, but in XPS it gets stronger due to the strong screening processes. At the bottom you see your experiment, and then you can see that the dynamical mean field theory and then projection to the cluster gives a very good description of your experiment. So that's nice. If you want to read about it, you can read the reference from Manas Giyashi and published last year. But now I will discuss the effects of this on X-ray absorption, and you can already see what's going to happen. We have a problem because 1s XPS spectrum has multiple peaks. So independent of exactly the nature of the peaks, it's obvious that there are many peaks. So this means that one photon energy, so this is an XPS spectrum taken 100 electron volts, let's say, above the edge. And one photon energy relates to many different electron kinetic energies. And this is not normally included in the density functional calculation because that takes a single kinetic energy. If you take FEFF, for example, or multiple scattering codes, you take a single kinetic energy. You assume that your photon energy and X-ray absorption gives a single kinetic energy, and you take that energy to do your multiple scattering. So just the shape of your XPS spectrum shows that that's not correct. So the conclusion from this is 1s X-ray absorption does not look like the empty density of states. So if you're doing KHs and you compare it with empty density of states, you might wonder, why do I not see this before? Okay, this I showed before. Maybe I can do this quickly. So this is the same graph as before. So your ground state is D5 plus D6 Leakant hole for manganese oxide. And in the final state of 1s X-ray absorption, the D6 Leakant hole state is pulled down below the 1s1 through D5. So you find two peaks, or actually then for the analysis of the XPS spectra, you find many peaks. So one photon energy yields two or more electrons with different kinetic energies. This is another example for iron oxide, and then we did 4 different configurations. So the conclusion is that K main edge corresponds to transition to empty density of states, but not by itself, but convoluted with a 1s XPS spectral shape. So what you would have to do if you want to do a good analysis of your K edge is you calculate the empty density of states with whatever density functional code you like for example FEFF. You calculate or measure the 1s XPS spectral shape, and then you do a convolution of the both, and then you get your X-ray absorption spectrum. Actually, this is the same, almost the same as the particle hole cumulant approach for inelastic losses from Joshua Kass in the FEFF code. So that effectively takes this inelastic losses, which are the tail, the satellites on the high energy tail. Another reason that you do not often see this is if you go to covalent systems. So I specifically chose very ionic systems, but if you take covalent systems, then the main peak in 1s XPS is dominating, so you hardly see your inelastic losses. So then you can go back to your density of states interpretation. So my conclusion for the K main edge is that you have an edge. You can do fingerprinting analysis on the shape, or you can do valency analysis on the edge. I will not discuss what the edge is because that will probably take 1 hour. If you do theory, you in first approximation say the empty states come from density functional theory, from whatever code you like. But if you have ionic systems, then the 1s XPS reveals incomplete screening, and that has to be incorporated into the analysis of the edge shapes. Okay, maybe this is a good moment to have a short stop again, if there are questions.
Sure. Neri, can you turn your mic on? I see you have a question.
Hi, Jerry.
Hey, Neri.
Thanks, Frank. So I have a question on your LDA plus U calculation you showed earlier, which qualitatively captured the pre-edge zones. So is that U included only in the ground state to capture the orbitals, or is it also included in the response calculation as well?
Yeah, I assume that it's calculated that it's both in the initial state and the final state. At least that. Amelie, you handed the calculations, but that would be the normal approach to take the same U in the ground state and then the final state.
Okay.
Of course, in the final state you have the cohort potential, which is another parameter in a way. Yeah.
Yeah, that's what I was.
Yeah.
Frank, this is TK Sham. I have a question for you. I just typed it out. I was wondering if anyone has done any XPS with the excitation energy very close to the threshold, so you may get satellites.
Yes. Yeah, that's. I did not touch upon that issue. So the XPS spectra I showed and we measured, they are excited at least 100 electron volt above the edge. But it's indeed a good question to see what happens if you measure XPS that will be very low kinetic energies, then closer and closer to the edge. Yeah, that will be that will be interesting. Of course, then you go into the resonant photoemission effect, which is a whole. It's a whole. Yeah, I mean, then you get a lot of additional effects, as you know, which are much more complicated to describe.
Okay, very good. Doesn't look like there's more questions. You should keep going, Frank. This is very nice. Thank you again.
Okay, so then the last topic I will touch upon is going back to the pre-etch and actually the non-local peak, so the peaks in between the edge and the pre-edge. Yeah, so this was my simple picture of the K-edge. So you have an exciton and an edge, but actually if you look more closely, there's something in between. If you take a system where you have isolated transition metal ions like cobalt acetoacetate, so cobalt 3+ low spin with 6 oxygens, octahedral, it's low spin, so T2G is full and EG is empty. So it's a very simple model system like titanium oxide. So you have one pre-edge particle due to the EG, there's no crystal field because T2G is full. And then you have your edge at higher energy. So that's clear. If we then go to another cobalt 3 low spin system, but now in a solid, then it becomes different. So this is low spin cobalt 3. T2G is full, EG is empty. At least that's the idea of lithium cobalt oxide. Then you see your pre-edge. This is a normal X-ray absorption spectrum. Pre-edge, then you see the edge of 7717. But there is something after the pre-edge, which is indicated with a question mark. If you do HERFD, it's not a question mark, but it's really a very clear peak. So you see your pre-edge, you see an unknown peak, and then you see your edge. So the question is, what is this question mark? There have been some papers in the 90s where they saw this, not a HERFD, but the normal X-ray absorption, and they took this as evidence for high spin, partially high spin, or at least not low spin, but that could solve the issue, of course, and this would be then a crystal field splitting. But actually, that's not what's happening. If you do a Ritz experiment, then it will become clear. This is first the idea of what's happening in the ground state of a transition metal oxide, indicated on the left in black. So you have the D states, which are partly occupied, and you have your 4 P states, which are empty, and you have your 1s state, which is occupied. Then in X-ray absorption, you excite a 1s electron, and then you have 3 options indicated on the right. So you can excite to the pre-edge, then you excite 1s 3D, and that's a local excitation on the metal, and that gives you a quadrupole peak. That's indicated in red Q, and the quadrupole peak is an exciton, so it's pushed out, pulled down from the D band, so that's why it's shifted to lower energy. If you excite to the edge, you excite to a P state, which is hybridized with the neighboring P state, so that's a delocalized P state, so that's quite clear also. But you can also do something else. You can excite to a P state, that's indicated in the middle on the right, and that P state, cobalt P state, hybridizes with oxygen P from the neighbors, but then with metal D on the next nearest neighbor. So it's a metal P state at the energy position of the nearest neighbor metal D state. So we call this a non-local peak. There are many different names for it, but so it relates to the D band, but it's a dipole transition, and it's the core hole is on one metal and the D electron is on another metal, so there's no core hole potential, or much weaker core hole potential. So it's shifted with respect to the quadrupole peak, although in the ground state it's the same state. And this immediately becomes clear if you do a Rix experiment. This was an experiment again by Georgi Vango. On the left, the isolated cobalt, so your quadrupole pre-edge and your edge. On the right, lithium cobalt oxide. You have your quadrupole pre-edge, you have your edge, and in between you have your dipole non-local peak. So you can, from angular dependence studies, you can prove it's dipole, and the pre-edge and the exciton is quadrupole. You can also see it's diagonal, so it follows the diagonal, so it's exactly the same as the edge. So actually, if you would do a density functional calculation, you will get this also at the P character to the D band. So this non-local screening peak is quite funny. So this is the calculation again by Amélie Juhain on the lithium cobalt oxide. Lithium cobalt oxide, it's a little bit more tricky because you have layers of cobalt and then layers of lithium. And the next nearest neighbor of cobalt can be in the plane of the cobalt oxygen, or it can be to the next plane. That's indicated at the bottom at the calculation of dipole E1. The high peak is in plane and the low peak is out of plane, but qualitatively it's the same idea. The quadrupole excitation is E2, and then you can see a clear shift between E1 and E2 due to the cohort potential. And then the calculation kind of reproduces the experiment with peaks alpha, beta, and gamma at the top. And so this is an example of non-local screening in lithium cobalt oxide. But this probably most of you know because it's some years old. But we encountered the non-local peak more recently again. And this is maybe more new to some of you. It's quite funny. This is the chromium KH of chromium oxide with circular polarized light, but you don't see any dichroism. And I indicated pre-edge structure and main absorption edge. So that's what you qualitatively would analyze. And then on the left, it's the Rix plane. But actually, this is not really correct. If you, I would do this analysis. You would never do this if you do X-ray absorption. The pre-edge actually is below 5990. It's not visible because it's very small in intensity. And what is called pre-edge is not the pre-edge, actually, it's a non-local peak. So because chromium is 4+, it's extremely covalent. There's a lot of holes on oxygen and then a lot of holes on the P character of the nearest neighbor chromium. So what is called pre-edge is actually not the pre-edge, but it's, okay, depends how you define pre-edge, but it's not the quadrupole peak, it's the non-local dipole peak. So why do I say that? You have to believe me now, but actually you can prove it from doing MCD in the Rix. On the left is the Rix plane of chromium oxide. In the middle is the same Rix plane, but now the dichroism. And you see that there's only dichroism at 599, just before 5990. So and then I indicated that on the left with the red arrow, so that's far before the, a little bit before the pre-edge, which is at 5992. So it's quite funny that at the pre-edge nothing happens, almost nothing happens in the dichroism. And you see the dichroism a few electron volts before. You also see it in the calculations. So at that energy, where you see the dichroism, you have your pre-edge. And then the intensity you see is the non-local intensity due to the dipole transitions. So here you can reveal it not from Rix, but from the magnetic circular dichroism in the Rix. Then another case is metal-metal charge transfer. So it's till now lithium cobalt oxide and titanium oxide and chromium oxide is all the same metal, but you can also see this feature if you do two different metals. This is ilmenite. And ilmenite, you have an iron titanium bridged by oxygen. So in the X-ray absorption spectrum, you already see these features if you know what they are. So they are peak A, B, C, that's the pre-edge. Peak D and E, they are the non-local peaks. So these are the titanium D states, which are visible in the iron KH. And then the comparison is made with iron oxide, where you don't have titanium and you don't have these peaks, D and E. This you can now nicely show from calculations. If you do calculations, you get these non-local peaks directly from your density of states. This is the density of states of ilmenite. At the bottom, the titanium D density of states, hybridizing with oxygen P, so that's very clear. Sorry. And then above that is the iron P density of states. So you can see that there's quite a bit of iron P density of states at the titanium D positions. And this iron P density of states is what you see in your KH. So this directly explains the two peaks in the iron KH. So it's quite funny that you can see titanium crystal field splitting in your iron KH. This could be called metal-metal charge transfer, although that's a bit dangerous statement, because that suggests it's an initial state effect, while in fact it's a final state effect. It's effect of screening in the X-ray absorption. Okay, that's what I wanted to say. So a very brief analysis of K-edges, focusing on screening. Pre-edges are self-screened quadrupole transitions that can be calculated with multiplets. The edge can be calculated with density functional theory, with the addition that the one photon energy gives multiple electron energy. So you have to convolute the empty states with the 1s XPS. And if you look very careful in your edge, you can see non-local screening in the pre-edges, including metal-metal charge transfer screening effects. Okay, that's what I wanted to say. Maybe there are some final questions.
Yeah, definitely there's final questions. Excellent, thank you. First question is whether in the past this extra peak had been assigned to shake up or shake down effects. Referring back to the cobalt oxide data, I think.
Yeah, yeah, it could be. Yeah, the story of shake up and shake down is for me very confusing. What exactly people mean? In my interpretation, shake up is the same as charge transfer, and in oxides. Of course, it's different in atoms, but in transition metal oxide. Yeah, I'm not sure if it has been assigned. If it's very close, I think people tend to assign it to crystal field and energy. There is one story I left out, which I don't understand yet. Maybe somebody else understands it. And that's the pre-edge structure of copper 3. I'm busy with that. There was a very funny paper published recently, The Mystery of Copper 3, which is completely wrong, I think. But it's difficult to prove how wrong. So, and it's something else than all the features I described here. So that's something.
Frank.
Yeah,
Frank, this is Lin Chen. I was the one asked that question. So I just want to see, for instance, like a TiO2, right? You see they're supposed to have a T2G and EG. However, you see the third peak. So that was assigned as a shake up, shake down. And also for the cobalt oxide, there's also extra peak as you show. So I just like to get your opinion on that. Thank you.
Yes. Yeah, thank you for the question. Yeah, so the titanium oxide, that actually was the first case, what I would call a non-local peak. Then you have your quadrupole transition to T2G and EG, and you have your dipole transition to T2G and EG. And then the funny thing in titanium oxide is that the crystal field is relatively large, it's 2.5 electron volts, and the screening of the core hole is also 2.5 electron volts. So the EG quadrupole exactly overlaps with the T2G dipole. But it has been analyzed in detail by many people, but for example by Delphine Cabaret 20 years ago, I think. I would call that non-local screening, or the shift between dipole and quadrupole. In copper 3, it's a little bit different, and also iron 4 or anything which has a, maybe I can say every system which is what we call negative delta systems. So when the charge transfer energy is negative, so copper 3, the third hole of the copper 3 goes to oxygen. So then you can also call it oxygen minus. The consequence of that is that there's an enormous non-local peak. So maybe that's the correct interpretation, but so then you say what is the large pre-edge in copper 3+ systems is the non-local peak again, and real pre-edge you don't see, or it's very small before the visible pre-edge. That's a similar interpretation for vanadium 5+, where also V2O5, where you cannot see the pre-edge actually, you can only see the non-local peak. But I'm not completely sure about this last part, so I left it out. But I'm working on this with at Solomon, for example, to try to resolve this issue.
There was a couple of questions about whether these effects can only be seen in solids, or if there might be a binuclear molecule where the same effects could be interrogated in perhaps a customized way. Any thoughts on that?
Yeah, that's a very interesting question. There's very few experimental data, as far as I know, on, but it would indeed be very interesting, maybe even the most interesting, if you take two different metals. And if you want to look at these states of one metal on the other metal, in principle it should be there, but there is an issue with symmetry. I did not go into that. If you're relatively close to octahedral symmetry, yeah, that depends what you say as relatively close, but that titanium oxide, chromium oxide, ilmenite, they're all relatively close to I mean, they are distorted octahedra, so that means that you dipole quadrupole mixing is not large. If you go to molecular systems, then typically they will be very low symmetry, so you will have very strong dipole quadrupole mixing. I did not go into that in much detail, but and then most of the intensity will shift to your real pre-edge. So the non-local peak might get lower intensity. Initially I thought it might disappear, but now I don't think that's true. I've seen recent data from Peter Glatzel, and it's not disappearing, but the intensity of the real pre-edge becomes larger, and then the non-local peak becomes more difficult to see. But it would be very interesting to do, ideally, HERFD experiments with high resolution on complexes with 2 metal or 3 metal.
Okay, very good. Neri, you had a question about HERFD?
Yeah, you were showing this HERFD plots earlier, and one thing I noticed, and I've seen this in other papers as well, is the pre-edge zanes and the HERFD overlaid on each other. The HERFD features don't perfectly match in terms of the peak positions. And you could get me some insights on that. Is it due to the slicing of how you do the HERFD, or is it some other physical? Is there additional physics in the HERFD?
Yeah, I think so. There's some things we don't really understand. It's not only the peak position, it's also the intensity. Yeah? So the intensity of HERFD is always larger than the intensity of normal X-ray absorption. And then you say, okay, that's because of the resolution. But if you broaden the HERFD again with your lifetime broadening, there's still too much intensity in the HERFD. And then several theories, ideas about that. One indeed could be that that what I think, but other people think something else. Other people being Peter Glatzel, so he's a real expert. One reason could be that your detector has indeed a finite width, and then takes a slice with, and then in that slice enhances the pre-edges compared to the edge. That's always possible, of course, if you take, but if you take the slice a little bit wrong, it might be exactly the other way around. So that's a tricky thing if you do only the HERFD. Of course, if you take the complete Rix plane, You can then later analyze it in detail. And then indeed there are differences in intensity and differences also in shifts. Yeah, that's true. Yeah, maybe as far as I know, that has not been resolved. It also depends a lot on which systems. It's also very interesting in actinide, this issue. And there are a lot of different interpretations and papers, but yeah. I think it's an open question, so it's interesting to get a real answer to that.
Thank you.
All right, there's been some back and forth in the chat about possible examples for the binuclear systems. Matthew, do you want to comment on that?
Yeah, Joe, I don't have anything yet in specific. Actually, I do. Like the reaction centers have things like manganese calcium clusters. And I know there's the cytochrome oxidase has, I believe, iron copper clusters. And so these are naturally occurring molecules where you have metal, oxygen, metal. But actually, there was another question before this exchange from Molly about nickel oxide.
Yeah. Hey, Jerry.
Hey, Molly. Sorry, go ahead, Molly. How are you today?
Good, good. Frank, thanks for this nice talk. In the, I guess like late 80s, there was work on lithium doped nickel oxide, where as lithium is put into nickel oxide, most of the charge compensation is supposed to take place on the oxygen, right? It's more or less like a negative charge transfer insulator.
Yeah, yeah.
But if you look at the K edge of nickel oxide, you really don't see a big lithium nickel oxide. You really don't see a big non-local interaction. Is that correct?
That I don't know by heart. I know a lot of the soft X-ray spectra on lithium nickel oxide, but not the hard X-ray actually.
So I mean, in a sense, if we were to do HERFD on lithium nickel oxide, would we expect to see a non-local interaction purely because the oxygen is charge compensating?
Yeah, yeah, no, that I would certainly, it would certainly be very interesting to look at that. Yeah, but I don't know by heart if that has been measured or how the spectrum looks like.
And will there be an effect? Because I mean, if experimentally, when you look at the nickel, there seems to be a yarn teller like thing because you have two different nickel oxygen bond distances from the XFs, which would be more like a traditional nickel 3+. So what would be the manifestation of this in the Zanes?
Yeah, that's a difficult. I mean, in general, the yarn teller effects are small in energy, so they will be difficult to see in K edges, I guess, or even in L edges. Yeah, no, but indeed the non-local screening effects will be very interesting. Should be very large in principle in these systems.
Okay, thank you.